Again, good afternoon, everyone. My name is Oleg, and I represent the Lacmus, or Litmus project. We are looking for persons who've disappeared using pictures from copters, using computer vision and neural networks. Our project source code is open source. The participants are developing it in their free time. So let's start with the problem setting. The problem setting is every year in many countries, people disappear for different reasons. The stats say that the number of people disappearing every day is more than 120,000 per Russia and more than 100,000 for the US. One of the most frequently encountered problems when it's about looking for people is when it happens in open nature. Quite often, people go hiking, lose orientation, and after that it becomes problematic to get out of the situation. For a person who've lost everything in open nature, you can identify the following risk factors. Factor 1, losing water, dehydration, getting no access. This time may be required to conduct a search and rescue operation. Hypothermia. At night, the temperature drops down quite low, and the opportunity to get warmer is usually absent unless the person is properly equipped. This reason is the most frequent reason for death of such people. Then trauma. A person who've lost in open nature tends to start panicking, which leads them to actions that quite often lead to trauma, after which their chances to get out of the situation dramatically go down. Panic. The understanding of the fact that the person is no longer able to get out of this location brings about a panic which reduces the chances of the person getting back to the civilization. The most widely used way to look for such a person is a search operation with ground searchers. Well, as usual, this entails a ground search party with the help of special services or volunteers, such as those that we have in Russia, Lisa Lertsova, Zapad, Sever. This search method is classic, time-tested, and at the same time quite effort-consuming, effort-intensive. You need to organize a lot of people. You need to organize search parties. You need to execute a whole lot of other tasks. Also, this method of search is quite slow. For instance, the search area of 500 by 500 meters can be covered by a walking search party in 4 to 6 hours, whereas you can have several such areas. Another way of search is to do search by copters using photographs. So you set up a course, a path for the copter. The copter goes along it, and in the predefined points it makes pictures, GPS-marked pictures. After that it comes back to the headquarters, where the copter operator replaces the battery, gets the card from the copter, inserts another memory card, and sends the copter on a new path. Through trial and error, we identified that the optimal altitude for such search efforts is about 50 meters, 50. This is higher than trees, but allows getting quite clear pictures where you can notice a person. On average, every search operation involves about 4,000 aerial photos. So viewing this number of operators, manual viewing, requires 6 to 7 hours at best. Also add the time spent on transmitting the pictures. So the low speed of image processing and unstable accuracy are the drawbacks of this approach. People can miss the lost person. So our development is the software that allows scanning these pictures using AI computer vision. So the software will only take about 1.5 hours on an average power laptop. So you can see high speed, stable accuracy, and the automation of the processing as benefits, as pros of this solution. A few words about the software that we have developed as part of the Litmus Foundation. It's an open source and a cross-platform foundation, so it runs on Windows, Linux, and Mac OS operating systems. We're optimizing our neural network, so it's going to run properly even at an average $500 laptop. The pipeline of using the software consists of 5 simple steps. Number 1, to copy the pictures from the drone memory card to your laptop. Second, run our software and indicate the folder with documents. Then press the process button, and that's it. It's the magic of the work. The magic has worked, and we get at the output marked pictures with people found. People are put in the frame. Then allow me to pass the floor to Georgy, who will continue the story. Hello, everyone. My name is Georgy, and today I will try to shed some light on how this magic works. Our app contains of several parts. One of them is the application itself that the users can install on their PCs. The UI is implemented using the Open Avalonia UI. It's an economical and cross-platform framework. Thanks to these technologies, our application runs on all modern platforms. The neural network is installed in the Docker container that allows relieving the user of a need to install specific drivers required for the operation of the neural network. And also, it allows easily manipulating the containers. All operation with Docker, all Docker operation is closed within the application, so the user doesn't need to know anything about the app. They can just use the app. Another part of our solution is the Web API. It allows effectively processing large volumes of data and getting the outcomes very fast. The web interface is built on modern open technologies such as Go, Python, Kubernetes, Redis, and Postgres, SQL, and so on, and is designed for high load. And finally, the core of our development, the neural network, based on the RedNet 50 architecture. We chose focal loss as loss function. This architecture is quite well known among machine learning engineers, and it's shown its efficiency in different computer vision tasks, so we took it as a foundation. We continuously work on the improvements of our identification outcomes, so therefore we make do a lot of experiments. So, for instance, we have found the optimum size of the picture. We've identified that if we reduce the size of the picture twice, we're going to get about the same accuracy, but the processing time is going to be reduced a lot. So, we've also ran a comparison with the FPN head. We used 2 approaches. The pyramid and the deep FPN. So the architectures are shown below. In the first place, we put the pyramid downward, where the image is larger. And in the second case, we removed the top levels of the pyramid And as to the low levels of the pyramid, we deepened them down. And these are the outcomes of our research. As you can see, the best way to deal with the problem is to use the deep FPM architecture. We've also tested this architecture on other computer vision problems, and we got the best results. Apart from the accuracy, we also need the speed, because there's no internet in the forest. So we optimize our neural network to run on netbooks and microcomputers. We tried and worked with different frameworks and devices, such as TensorRT, OpenVINO, Jackson Nano, Intel Movidia, and even the results of inference time research are shown here in this slide. Passing the floor on to Oleg. So, because of the specificity of the problem being solved, we had to organize the data set ourselves with the required pictures. This is the way we got our own data set, Litmus Joe data set, or Lacmus drone data set. A link to it is available in our project site. Because this project was run by the participant free time, we need support. And here's the list of those organizations that provide such support. Novaya Gazeta, which is a Russian newspaper. Teplitsa, Technologies for Social Good Initiative. ODS AI, it's Open Data Science. It's the largest Russian language community of data science researchers in machine learning for social goods. Lisa Alert, a voluntary search and rescue team. JetBrains, the authors of great tools for developers. To teach a neural network, we needed serious computing power. For our calculations, we use resources in the first Russian immersion-cooled data center, Immerse Cloud. At present, our solution has already found more than 100 people who had been lost. You can join us in GitHub on this link, and a Telegram here. So all the best to you. Please don't get lost. Regarding the questions, I would like to specify. Quite often, people ask the question, isn't it easier to put a heat sensor on a copter and look for people using this? Well, I know the answer to this question, but I think we need to explain why this is not a panacea. So, Georgy, well, I'm thankful to you for the answer. Yes, Oleg, of course I'm prepared to answer this question. It's all very simple. When a person gets lost in a forest, their body temperature is not just like with a regular person, 36.6 degrees Celsius. So the heat sensor will just not notice it. Second, people wear clothes. And these clothes have about the same temperature as the ambient temperature around them, and this also tends to hide people. And third thing, heat sensors are quite expensive, so putting them on a drone, I mean, not every search and rescue team can afford that. Okay, accepted. Good. Yes, there are lots of difficulties about using heat sensors. So thank you very much. Our session, AI for Social Good, runs to a close. We have heard the last presentation in this slot. So many thanks to all the speakers for the participation. I'm Oleg Dryupin, AI for Social Good. Socially aware artificial intelligence. Thank you, everyone. See you.